All right, we're on.
We're on. Welcome everybody to session number 2. We got a bunch of great questions this week, so we're going to launch right into it. And the first question is, how much time would it take to be fluent in Python? Which is a very challenging question to answer.
It is, and it's challenging for a couple of different reasons. There's the term fluent. So what do you mean by fluent in Python? A general description of fluent, in my opinion, would be you feel confident and competent in your ability to solve problems that you've never encountered before using this language to do that in. So these might be, complex problems like, creating a payroll system for a company that has 200 employees, and maybe those employees are of like 4 different kinds. Maybe you've got salaried employees and hourly employees and part-time employees and contract employees. So, and then the other aspect that makes it challenging is it depends on what you mean by time, right? Because you can't really measure it in terms of like this many weeks, this many months, this many years, because it depends on what you're doing in those weeks, months, and years. So it's going to be an experiential thing. I think it would be similar to asking the question, how much time would it take to become fluent in Italian or in Japanese or in Russian? Right?
Yeah, totally.
So, and I suspect it would take a similar amount of time, a similar amount of effort. And there's no shortcut. There's no substitute for you got to sit down with people who speak Italian and try to have conversations with them and learn new words and new idioms, and how natural or fluent speakers of that language use those words and idioms. And the same thing's going to happen in Python. You're going to need to spend a lot of time working not fluently in Python, and slowly building up your fluency. So I would say if someone were earnest in their desire to learn Python and wanted to become fluent and were willing to spend, say, 40 hours a week consistently, I would say, and had no prior experience in programming. So you're also learning programming concepts, simple computer concepts on top of that. I would say somewhere between a year and 2 years.
Yeah.
Does that feel?
Yeah. That's a year, between a year and 2 years of full-time work.
Yes.
Right. And the reason why is because any programming language has a sort of, you learn the language, you learn the syntax, you learn how to express basic ideas, but much more learning a language and becoming fluent in it is learning how to solve problems and express yourself across a wide range of contexts. And that's the part of learning a language that takes the longest, is learning all these different contexts and what the best way to express yourself is. I wouldn't say, I think I'm like barely fluent in Python as an instructor of Python. I'm still learning new things about the language and all these weird little dark corners that I don't know much about. Phil is always teaching me new stuff about it and how I can do things more clearly and more effectively using certain language constructs that I wasn't even aware of, right? But I feel like I can almost invariably express myself effectively using the Python language at this point. But that doesn't mean I've stopped learning the Python language, right?
Right. Yeah, there are definitely levels above fluency.
Yeah. Yeah.
So it would be the difference between being fluent in a language like Italian or English and the ability to be creative and artistic in those languages, maybe to write a novel or a poem or a play or something like that.
Absolutely.
I would also say that if the starting context were different, then maybe you already know how to program very well in a language like C or C++ or Java, then learning fluency in a new language like Python is going to take much less time.
Yeah.
So if you are already fluent in one programming language, Gaining fluency in another similar language like Python would probably take less than a year in that case. And if you're already fluent in, say, 2 or 3 programming languages, gaining fluency in a programming language like Python might take you only a couple of months, as long as you're dedicated and focused on that goal over that amount of time. So there's a lot that you gain from learning one language that applies directly to things you're learning in a new language. And then as you acquire, and for people that are multilingual, I think they experience that as well. Once you've learned a couple of spoken languages, picking up a third or a fourth tends to get a little easier.
Yeah, and this actually helps answer the last question on our list. I've seen courses that want you to be familiar with a list of 7 or 8 languages. Do you find more value in delving into a few languages, or is it better to get familiar with a broad spectrum of languages? Is there an optimal number of languages to learn? And the the answer really is, it depends on what you want to do, right? Because all of these languages are sort of industry specific, right? There's certain applications that are better for certain types of language, like database languages and web programming are 2 things that go together super well. And learning JavaScript and MySQL, those are totally different languages, but they interact in a specific application of building the web pages and services that we use all the time. Python is like a general purpose sort of scripting language. They call it glue code because it connects a lot of different kinds of systems and runs different things in the background. C and C++ are foundational languages that run operating systems and the hardware and the silicon that's all around us. And that way it's kind of purposeful for whatever it is. Learning one language helps you learn other languages down the line because the patterns of looping and decisions and sequence and all that kind of stuff, data management, memory, all those concepts are roughly applicable across all of these different languages. They do them slightly differently, but once you learn them, you don't have to relearn them every time you learn a new language. You just learn how to say it in that language.
Right. And you can infer from the structure of this course that we have some opinions on the subject of number of languages, because we built 2 languages into this course.
Yeah.
So we must be of the opinion that 2 languages is better than 1. And from a beginner's learning perspective, the reason we took this approach is we think that Python provides the shallower ramp for the absolute beginner, and we can start to do meaningful and interesting things more quickly and more easily in a programming language like Python, and start to gain an understanding of the concepts. And then halfway through the semester, when we switch over to Java, which is a syntactically more complex language and structurally more complex language, we're going to re-explore a lot of those same concepts in a new context, and you get a sense for how the computer science is the same, what we're asking the computer to do and what the computer can fundamentally do are the same, but the 2 languages provide 2 different ways to express those ideas, and it gives you a sense for the diversity in programming languages out there. There's a rule of thumb that's offered to people who want to become professional programmers, and that's you should learn 1 new programming language a year. So if you completed a computer science degree and went out and got a job as a software developer, it should be on your to-do list, pick a language this year and spend this year learning that language and attempting to gain a level of fluency in that language. And then next year, pick a new language. And your choice of which language to pick should be based on what sounds interesting to you, or what kind of things are trending in your industry or in the areas that you're interested in applying these concepts. So, but I don't think there's a specific list of N languages that people should learn.
Yeah, totally. It's really dependent on your career goals and what you want to do with the programming skills that you have. Let's shift gears a little bit here. Can you tell me how programming relates to my favorite video games such as Skyrim and Shadow of the Colossus? I signed up for a video game design course for fun, and I was just curious how programming, if applicable, makes all those amazing graphics. So this is So in my view, video game programming is one of the most challenging applications for programming because there is a lot happening behind the scenes to make those amazing graphics that you're seeing. One of my first jobs where I was actually doing programming, I was helping build a three-dimensional simulator for robots to run around in. And what we ended up doing was basically building a game engine. So we had three-dimensional rendering, we had physics built in, we had to do shading and lighting and graphics and all kinds of stuff to make it look realistic and have it behave realistically. We were doing lots of math, we were doing an incredible amount of programming, and all of that stuff, the entire game is programmed in some language. All of the graphics are very specifically programmed to be efficient, and they have to go fast to make it pretty. Otherwise, you get lag and you get screen tearing and all kinds of terrible things and stuff like that. And all of it, you're exercising every muscle that a programmer has in order to get a video game up and running, or just even a little part of it up and running. So lots of programmers are involved in developing video games. That said, it's also a very competitive market. So lots of new programmers want to make video games because they play video games. And the companies have a lot of applicants, and you have to be an excellent programmer in order to sort of beat out your competition and get up, climb that ladder. So it's a big industry for programmers.
Absolutely. Okay, so the next question is, can you give any good resources on learning assembly language? And is there any reason to learning assembly language? Because it seems to be a dead art.
So assembly languages are the, as we talked about in the class, assembly languages are the lowest level language that a computer understands. And this is what we call, it's also known as the machine language. And it is whatever the chip itself understands as instructions to execute. And often they're super fine-grained, like move this piece of memory to this piece of memory, or add these two numbers together and then put the result somewhere else. Stuff like that. Very, very basic stuff. And what the advantage of knowing these languages these days is what comes into another one later. Another question later is you get to make things very optimized. You get very efficient code when you write it yourself in assembly language. The compilers and interpreters that we're using in our class are built for general purpose. So what they do is say, when you want to do an assignment statement, it has a template for that assignment statement, and it just sort of fills in the blanks. Where are we taking the data from? Where are we going to put it? And it uses a block set of instructions, and it just plops those down and fills in the blanks. That may not be the most efficient way to do it in every single application. So when you learn an assembly language, you learn how to look at a big task, break it down into these tiniest little pieces, and figure out how to manipulate them so that you don't have to do as many steps and you can get it to go really fast. This is very, very applicable in extremely high performance applications. One that we just talked about was video game graphics. They call them shaders. The programs that do all of the rendering for video game graphics have to process millions or billions of polygons a second, and they have to process it very quickly and do very complex operations to these things. So often those are written in assembly language so that the programmers can tune it down to a single cycle. If I can get an extra computer cycle out of a shader, and I'm running that shader a billion times a second, then I get, an extra few billion cycles that I can do something with, which is really very, very powerful. So you can really make high performance applications run quickly if you learn assembly language. How to go about doing that is much more challenging because there's not a lot of learn assembly courses online. Part of a computer science program is to learn some of the basics of assembly line language or assembly languages. And there might be specialized courses at your community college or possibly some other online resources.
We can do a little bit of research and see if we can find a couple of good online resources or text resources and post those as a reply to this question in the discussions.
Yeah.
Another reason to learn assembly languages outside of their applicability is the level of understanding of the machine that they will give you. So in order to program an assembly language, you have to understand at a very fundamental level what the computer is capable of doing, and you're instructing the computer to do those things at an extremely fundamental level. And this actually benefits you when you're writing programs in a higher level language like Python or Java, because you realize that when you're asking the computer to do something like, print the evaluation of this expression, you already have this sense of, I'm actually asking it to do quite a few things here. This is an amount of work for the computer to do. And you might start thinking to yourself, I could optimize my own high-level program a little bit by restructuring this or simplifying this so that when it gets interpreted into the machine's instructions, the machine can do that more efficiently. Or you'll realize why doing things a certain way takes twice as long for the computer as doing them another way. So if you are going to be fairly hardcore in computer science, it's worth studying at some point. I don't think you have to be necessarily fluent in it unless you're aiming at a career that directly leverages that. But it is nice to know.
Yeah, absolutely. What are the pros and cons of using high-level versus low-level languages? Is coding in the lowest level to optimize programs a niche skill, or are there lots of viable jobs like this?
So I'll start with the first part of that question. The pros and cons of high-level languages versus low-level languages. So low-level languages allow you to focus on instructing the machine in specific detail. So if you not only want to tell the machine what to do, but specifically how to do it, then a low-level language is what you're going to need. High-level languages have the advantage of allowing us to be a little more generalized when we're instructing the machine, and we can tell the machine what we want it to do and allow an interpreter or a compiler to figure out how the machine is going to do that specifically in its machine language. So you end up with, say, for instance, a program that's going to take 2 integer inputs from the console, compute the sum, and display the result. In a high-level programming language like Python, that's 4 lines of code.
Yeah.
What would that be in assembly language?
Oh, geez, hundreds and hundreds of lines.
of individual instructions.
Of individual instructions, because there's a lot of processing. You have to set up I/O. You have to do all kinds of manipulating of information, and everything. All of this has to be done in both of these cases. It's just all of it is hidden and abstracted away in a high-level language. So you can express yourself very effectively, but in an assembly language, you get all the detail, right, that you have to deal with.
So high-level languages in general will allow you to accomplish more in less time and with less code, less keystrokes.
Yeah.
But you're trading away some of your ability to optimize or instruct the machine to do things in a very specific way.
Yeah.
Which, for the vast majority of applications, is not a problem. I mean, the machine, these machines do what, about 3 billion operations a second?
Yeah.
So if it has to do 3 times as many operations as the equivalent assembly language instructions, so maybe the program takes, a second to run instead of a third of a second to run.
Yeah.
And for most human needs, that's probably acceptable. And the difference is going to be writing that program in 15, 20 minutes an hour, or writing that program in
a couple weeks.
So definitely advantages and disadvantages on both sides, but you can see why the high-level languages are very popular these days.
Yeah, yeah. And there's always the opportunity in a lot of these high-level languages to dip down into a lower-level language to take advantage of that optimization and that level of control. So that exists. That's a real thing. The other problem with low-level languages is often you're tied to the hardware platform itself. So like assembly languages and C and C++, these are compiled languages that we have to have a specific compiler, we have to have a specific interpreter that is tied to my x86 machine, which is like a desktop or a laptop, or to an ARM processor, which is like what's in your phone, or to something else, which might be in your car or something like that. Those languages, a piece of code written for one platform cannot be directly translated or just ported to another platform. You have to rewrite it for every platform you're going to use it. The high-level languages abstract that away and allow you to make portable code that runs wherever that language runs, like Java and Python. Those are examples.
Yep, that's a good point.
Yeah.
The second part of that question is coding in the low level to optimize programs a niche skill? From my perspective, I don't experience it very often. I'm a business application developer. I'm working with the highest level languages I generally can. And my advice to customers is, if this isn't fast enough for you, buy better hardware. It's cheaper. Better hardware is cheaper than paying highly skilled assembly language programmers to write optimized code that's going to take 4 or 5 or 10 times as long to write, test, and debug, just to eke out maybe a factor of 2 improvement in the performance. It tends to be better to just add more cores to your server.
Yeah, totally, absolutely. And I think it is a niche skill very much. I also think it's one of the highest. Being good at low-level programming is one of the highest level skills that you can have as a programmer. So this is like somebody that's experienced, that's been doing this for 10, 15 years. They've seen everything and they know how everything works all the way down to the nitty-gritty, and they've been doing it for a very long time. That level of expertise is very rare, and there's not many people that do it. So if that's your goal, go for it, but it's going to be a long road to get there. But when you're there, you have you basically have all the power of the machine at your disposal, and you can make it do things that seem impossible from a high-level programmer's perspective. And there's absolutely a market for it. We talked about video game programming. Google employs a lot of these people to help run and optimize the core algorithms that run their services. Facebook does the same thing. All these large software companies, they're the ones that invest in making the billions of machines that they have run more effectively and provide the services cheaper than they were doing before. So it's kind of the other side of the coin, is after you've thrown as much hardware as you can buy at it, how do you make your performance, your service level go up? From there, that's where the optimization comes in.
Cool. Yeah. I love this next question. This next question is, who creates new languages? And then subsequently, what's the best track to developing the skills and finding those jobs? So there are hundreds of mainstream programming languages today. And then there are thousands of obscure, some of them are even just comical, programming languages that were created for fun and for jest.
Yeah.
But so if we just focus on the ones that were created and are mainstream, who creates these languages? It's an incredibly diverse group of creators. Government agencies have created programming languages. Entities like Google and Facebook have created their own programming languages, and computer science students have created their own programming languages. The Python programming language was created by Guido van Rostrum when he was on Christmas break from school in his, I believe, his graduate degree. And he was just looking for something interesting to do, and he started putting together the Python programming language over that Christmas break, and then just continued to work. And this was in the early 1990s.
Yeah. So anybody can create a language, and it can grow if it's promoted and it fills a need. It can grow to be as popular as Python and stuff like that. The C and C++ languages, their foundations are at AT&T. Um, Java is a consortium, was developed by a
Sun
consortium.
Microsystems originally,
Right, yeah.
And Oracle owns it now.
Yeah, Oracle owns it now. And JavaScript is a weird one because that's a programming language developed by committee, right?
It is managed by a committee now, but it was originally made by the Netscape people.
Oh, okay.
As a browser scripting language.
Right. So all of these things come from all over the place. And anybody can do it. So as part of, like, in our computer science program at ASU, part of the curriculum is a class on it's computing theory, and they talk about how languages work, how they're defined, how you can create your own, how you develop your own compilers, because that's the other side of a language is you develop a standard for how to communicate with a computer, but you also have to do the thing that interprets that communication and actually runs instructions. So that compiler or interpreter is the part that you develop when you're developing a language, and because it allows you to actually write programs that execute. So that's part of the computer science theory part. And being really good at that and being really effective at that is another high-level skill for people that learn programming in computer science.
You know, the extreme impractical end, you have programming languages like Whitespace. Have you heard of this one?
Yeah.
So it's a programming language that that you code in all spaces, tabs, and returns.
Yeah.
So the code is not even readable. It just looks like a blank white page. But those combinations of spaces, tabs, and returns interpret into instructions for the machine to follow.
Yeah.
Obviously, no one in their right mind would want to try to solve problems in a language like that. So that language was just constructed by someone who was, interested in experimenting with this and obviously wanted to come up with the most comical and impractical, but usable programming language that they could.
Yeah.
And there are other and probably worse examples than Whitespace.
Yeah. Whitespace, programming in Whitespace is like, you can imagine trying to program using Morse code in invisible ink. That's what programming in Whitespace is. Think about how complex, how hard that would be, and that's what programming in Whitespace is like. Cool. The next one is, what kinds of languages do microprocessors like Arduino and Raspberry Pi use? Are these examples of embedded systems that Ryan works on? That is absolutely correct. So Arduino and Raspberry Pi. We'll talk about Arduino first. So Arduino is a small embedded systems platform. It's a little tiny processor on a little board that you can plug power. You write a little program for it, load it on, plug power into it, and it runs that little program forever. And you can plug like sensors and motors and lights and switches and all kinds of cool stuff into it and make a little product that does a thing. The Arduino environment is based on the C programming language. And C is super common for these types of systems. We would call them embedded systems. Because these embedded systems are computing resources that are embedded in other products, and they do one specific thing for their entire life, as opposed to doing 1,000 generic things like our desktop and laptop computers do and our phones do and stuff like that. So these big machines we're used to are generic processing systems, and embedded systems are the products that do specific things for us. Most of those are programmed using the C language because that's a very low-level language. It works very close to Silicon, and we get a lot of control over the system. Not as much as assembly language, but much more than like Java or something like that. Raspberry Pi is kind of weird because a Raspberry Pi is a very sophisticated embedded system. It's running Linux, which means that it's got a full-blast operating system. The Linux operating system is written in C, so that's part of that's there. You can write programs for the Raspberry Pi that are written in C, but the Raspberry Pi environment, that Linux distribution, also includes a Python interpreter. So you can write high-level Java and Python programs for the Raspberry Pi. It's powerful enough to run those interpreters pretty efficiently, and you can write programs that interact with it that way. Raspberry Pi is a great way to get started. That's a great bridge to embedded systems if you want to finish this class and are excited about working with it later on in your explorations.
Cool. This next question is a really good one too. Could a program be written to help a computer estimate syntactic errors and self-correct, kind of like autocorrect for Microsoft Office or Microsoft Word applications? Can this be done for programming? The answer is yes, and it is being done in your heavy-duty professional integrated development environments, the tools that professional programmers tend to use to develop software applications, things like Oracle's Eclipse and Microsoft's Visual Studio. These are very sophisticated programs that allow you to write code in a programming language like Java or Python or C++ or C#. And as you are typing the code, they'll be doing static syntax checking, just like if you're typing a document in Microsoft Word and you misspell a word and it underlines it in red, and then you can right click on it and it gives you a list of options. That same kind of thing is going on in these sophisticated IDEs. That kind of functionality, it's generally called IntelliSense, or it falls under the umbrella of a term called IntelliSense, which was, I think, actually a Microsoft registered trademark, but we all just kind of use it generically now.
Yeah.
But it is that kind of autocorrect for programming. When we talk about estimating syntactic errors and self-correcting, that becomes problematic because when you're writing something in English, it's much easier to create a system that suggests synonyms or words that are spelled similarly, and maybe do some auto correction of that kind of stuff, because you can be fairly confident that you're going to end up with the same basic meaning. But when it comes to writing programs in a programming language like Python or Java, basic meaning isn't going to cut it. It has to be specific, it has to be complete, and it has to be correct. And any deviation from that is going to be a problem. So having the computer self-correct means that the computer would have to make an assessment of what it was you were trying to do and guess that correctly. And that's a very dangerous thing to put onto the computer when we're writing programs that need to do very specific things very quickly, very accurately, like maybe schedule flights in and out of a busy 2-runway airport, or route ambulances to an accident scene, or navigate autonomous vehicles. If the software auto-corrected what it thought was a mistake in a particular way, and that wasn't the right way to correct it, that's going to be a huge problem. So we're still at the point where we have to have human eyes on this stuff. Ultimately, a programmer has to make the decision. We might have a situation where the program can look at your code and say, this isn't right. Maybe it's one of these things that you're looking for, but you're still going to have to say, yeah, it's this one, or no, it's none of those. That being said, I'm open to the idea that in the not too distant future, within certain narrow domains, we might have systems that can write complete programs to solve specified problems that we might actually have enough faith in to allow them to do that unsupervised.
Yeah, so, which is mind-blowing.
It is.
Yeah. Cool. And our last pre-prepared question, we've got a couple in the chat room that we're going to answer here in a minute, is what are code libraries, and do you use them personally? So a code library is an archive of functionality that has been pre-written either by yourself or by somebody else that you can deploy across a wide variety of specific applications, right? So some common libraries are things like the standard template library that you guys are getting used to, or not the standard template library, the standard library
for Python, yeah.
For Python, the standard library for Python, which is a set of functions, a set of behaviors that are ready and easily deployable across a lot of different programs, right? So it's stuff like you're using print and you're using input right now. And those are written by somebody else in the past, and they're written in such a way that they're useful across a lot of different programs, and you can use them whenever you want, basically. We just finished writing a set of libraries that help us do auto grading in Vocarium last semester. So at the end of the fall semester in December, we finished our libraries and rewrote all of the assignments to help give active feedback to you guys as you submit your things. So the things that are doing stuff like checking whether your program actually executes and if you're using the right variables and stuff like that, those are libraries that we've written, and we hope they're working out because this is the first time they're being deployed for us. But we use libraries all the time. It's a great way to write programs, to write sets of code that are usable across a wide variety of domains and specific problems.
Virtually all modern programming languages, programming languages that are in standard use today, come with what's called a standard library. So C comes with a standard library, C++ comes with a standard library, Java comes with a standard library, Python comes with a standard library, and these libraries could include hundreds, thousands, or even tens of thousands of units of functionality. And so what they are trying to do with their standard libraries is provide a set of pre-built features so that you don't have to reinvent the wheel. So if you're trying to create, say, for instance, a game in Java, rather than having to write the code in Java to create a window on a graphical user interface system like Windows or Mac OS or Linux, that's already been built for you. There's a library that has the code that will create that window for you, and all you have to do is import that module from that library and execute that code, and the window's created for you. So what would have taken you possibly thousands of lines of code now takes you 2. And then beyond the standard libraries, you have special purpose or third-party libraries. So for the things that are not as common, that not every programmer necessarily wants to do, maybe particular domains, maybe you wanted to do natural language processing. You wanted to write a program that crawls the internet looking for news articles on climate change and compiles those into a summary. And you're going to need to do some natural language processing to identify which of these articles in the news are actually relevant to your search, and then some way to combine that information into a useful summary. That's not something that's super common amongst programmers, but it's common enough that somebody's probably already written a library that does most of that. So you could find that third-party library, import that into your, there's probably one for Java, there's probably one for Python. And then this is going to make your job much easier because someone's already invented that wheel for you.
Yeah. Awesome. Okay, so we got 2 more questions from the chat room. As we answer these, if you guys have any more questions, please post them there. Otherwise, once we run out of these 2, we're going to sign off for the week. But the first question we have is from GL, and they say, after completion of this course, do we have further classes from you? I want to continue more advanced courses with you after completing this. It's awesome that you're interested in continuing to work with us, especially at this early stage in the class. Unfortunately, through edX, we do not have any additional courses available yet. We may in the future, but we don't know for certain. We teach classes on ground primarily here at Arizona State University, so you can always come and join us here if that's your thing. But unfortunately, we don't teach any other online courses besides CSE110.
Right. I'm teaching on campus here this semester the follow-up course to this one, which is CSE205. And we just wrote an application in class yesterday where we had Godzilla battle Pikachu. Godzilla won 7-1.
So Pikachu won once.
Pikachu did win one.
Awesome.
Yeah.
Excellent.
So
fantastic.
Big upset.
And Fahad asks, how can programming help electrical engineers? What do you think about that one?
Well, I mean, so to me, I go very fundamental when it comes to this question of how can programming help. And to me, the fundamental answer to that is the purpose of programming, the purpose of computer science is to make things smart or to automate intelligence. So if there's something that requires intelligent activity, the kind of thing that humans have to do. So if there's something you need to do in your field as an electrical engineer, and it consumes time and effort, yet you can describe the process to do it, then you could write a computer program to do that and make yourself much more efficient and productive. So an example from my personal experience is I teach a particular class here at ASU, and twice during the semester we do peer evals. And so I have a class of 40 students in teams of 4, and each member of each team has to evaluate themselves and the 4 other members of their team, and that generates 160 individual evaluations, which then have to be collated, combined, summarized, and distributed. In the first semester I taught this class, it took me 3 or 4 days to complete that process because I did it by hand. The second semester, I spent 3 or 4 hours writing a program in Python that does it for me, and now I push a button.
Yeah, it's an amazing, learning to program can be an amazing time saver for many careers. In electrical engineering specifically, you're going to be doing a lot of analysis. So you collect a lot of data, you process that using electrical engineering processes like figuring out frequencies of things and phase distributions and all kinds of crazy stuff. And that's a lot of math that has to be done and repeated across a huge amount of data, which is absolutely perfect for computers. So part of the electrical engineering program here at ASU is that you learn to program in MATLAB, which is a mathematical programming environment, and you write programs that help you do this analysis for very large systems. This is incredibly common across all kinds of engineering, is using programming to do the analysis that we used to have to do by hand. You still have to learn the principles, but you don't have to. It's like trying to do math without a calculator. You don't want to do that anymore. Nobody wants to do that since you've got a calculator. So we use calculators, we use computers to do even more of that processing for us and to come up with answers that we can then use to help design better systems. So that's the gist for not just electrical engineering, but all engineering and many careers as well. One last question. Can the students create a group in an instant messaging app like WhatsApp? Absolutely. We're not going to set that up for you guys. Our primary mode of communication is going to be through the discussion boards. But if you guys want to talk to each other and help each other out through other channels that you think would be more appropriate, please go ahead and do so. But remember that don't share solutions to things. We want everybody's work to be unique in their own and representative of their own knowledge. So help each other solve problems, but don't share assignment solutions and things like that. That's the bad side of sort of group work. So we don't want you to work in groups on assignments. We want everybody to work individually, but we do want you to sort of help each other out and be a good learning community together.
Absolutely.
Okay.
All right.
Awesome. Thank you guys. Keep up the good work, and we'll see you in the discussion boards.
Bye.